Hello everyone. In this opportunity, we are going to socialize our paper titled Sign Language Recognition using lip motion based on time frequency characterization and conventional machine learning techniques, whose members are Manuel Alejandro López, Dagoberto Mallorca Torres, Diego Pelufo Ordóñez, and myself, Diego Andrés López. In this section, we present a disclaimer to refer to the copyright of the pictures presented. Introduction. Worldwide, about 5% of the population, 430 million people, suffer from disabling hearing loss. Sign language is the natural language of deaf people, and it has linguistic roles that involve non-verbal language based on corporal gesticulation and hands. The communication is based mainly on the manual expression of the orientation of the hands and its position relative to the body, and the local configuration of the fingers. Most of the population does not understand sign language. It's a barrier that prevents expressing the communicative and non-communicative needs of the human being. Technological advances have enabled the development of devices that recognize hand gesture space, but these require a classification stage. The classification algorithms are divided into two groups: machine learning (ML) techniques and more sophisticated deep learning (DL) techniques. In consequence, ML techniques are of the interest of the scientific community because of their lower computational cost and good classification performance. In frequency extraction, we use discrete wavelet transform, DWT, and following the morphology of time series, which refers to a successive decomposition of frequencies from which coefficients are extracted to represent them. Finally, we experiment the proposed methodology with the dataset American Sign Language Lip Motion 25 subjects 6 designs. In the next stage, we will refer to materials and methods. For the development of the methodological proposal based on conventional ML techniques, it's necessary to develop some stages such as database selection, data cleansing and segmentation, data transformation and sampling, feature extraction based on discrete wavelet transform (DWT), and classification and experimentation with multiple algorithms. User disposition for data acquisition. Regarding the workspace, it describes the space that the user has to perform gesture capture by LMC device. Says that the interaction box is a boundary area where respect precision sensor is the highest, as shown in the picture. To validate the proposed methodology, we use a dataset that has been previously validated by other authors as a reference. This dataset contains captures of 60 different American Sign Language (ASL) signs from 25 subjects and about 1,700 signs in total, with one hand, left or right, and two hand gestures. To learn more about the dataset, a summary statistic is performed to allow visibility of the normal range in the data, which is shown in the table below. The dataset is composed of data of the three-dimensional coordinates x, y, and z of the different reference points that the device captured for each hand, as shown in the figure on the right. We present the comparison of the visualization of the gesture 5 of the data from the dataset, and the recreation of the visualization from the EP of LMC device and the hand in real life. The original dataset has missing values, null data, and inconsistent data, So we perform a frame by frame search for empty frames and coordinates of reference point that exceeds the mid-range values of each gesture. The graph below shows the hierarchy of the data organization to give an idea of the search work, with 25 folders, 120 files of 60 gestures, one for right and one for left, and frames depending on the gesture, and more than 80 columns of characteristics as coordinates. At the time of capturing the data, the same capture is performed n times a gesture, so it was decided to segment into equal proportions, given a global statistics of the number of total gestures presented in dataset. Data transformation and sampling. The data captured by LMC device are absolute position measurements regarding a coordinate system located on the device. Hence, the behavior of the model is limited by the distance from the hand making the gesture to the device. Therefore, we transform the absolute coordinates into relative measurements with respect to a point in the palm. In the data transformation and sampling stage, we have the fundamental change for the adaptation of our methodology. The tables below show the original organization of the dataset as well as the proposed restructuring. In the original dataset structure, each column represents the x, y, and z coordinates independently for each reference points of the hand, while in the restructuring, all coordinates are arranged continuously in the time that makes it a time series. The time series of each gesture don't have the same size and duration, so we obtain the average frame rate of each gesture and resample all the captures to the higher dimension, which is 96 frames. The classification algorithms to be used are from ML, so we require the feature extraction stage. In addition, given the dataset extension that has a large amount of data, and the need to couple to the time series architecture, the discrete wavelet transform (DWT) is carried out. Employing this technique leads to 180 features instead of 82 features for each frame used in the gesture. In the classification state, we have used the C# Visual Studio ML Model Builder toolbox, an interface that automatically explores the different algorithms and their ML configurations parameter by way of hyperparameter selection, which greatly simplifies the classification task, whose operating methodology is based on the diagram shown below. For the given ASL dataset, the recommended models are the following: stochastic dual coordinate ascent (SDCA), light writing boosting machine (LGBM), and fast Ryoba. In the next stage, we will refer to results and discussion. As you can see in the example shown below, we have graphically described the process that comprised the methodology. First, we have plotted the original coordinates with respect to the number of frames for 5 examples of the gesture 0. Throughout, the organization raised in time series to subsequently have the wavelet characteristics that describe such data in a summarized way. In order to evaluate the influence of the multiple stages of the methodology and the classification performance of each of the proposed algorithms, different experiments are carried out based on the possible combination between the data restructuring, data balancing, and feature extraction with DWT variables. The most relevant results are shown below. Based on the previous explained experiments, the method selected is number 4 with FAST3 algorithm. We compare it with the models from the reference study that employ DL techniques. Finally, we have the conclusions that are obtained from the realization of this research work. The study develops a low resource system with the time series and DWG offering acceptable results. Possible future works to improve the results, such as a support of sign language experts and add automatic segmentation or other characteristics that allow the recognition of the other sign language. The use of conventional ML models and their easy-to-use algorithms avoids the excessive consumption of computational resource compared with DL network models, and ML models allow streamlined training based on good filtering and structuring of data. Thank you very much for your attention.